let's talk about differentiation and integration of power series. So let's take a power series, c sub n times x minus a to the n, centered at x equals a with a radius of convergence greater than 0. Now that radius could be finite or it could be infinite. So here's the way we would write it out if we wrote it out in its expansion with the constant term c naught plus c1 x minus a to the first, c2 x minus a squared, and so on and so forth. And it will be differentiable and therefore continuous on the interval from a minus r to a plus r. And this is how we can take the derivative. So let's just see where that's coming from. If we take the derivative, the constant term is going to be 0. So when we take the derivative, the constant term is 0. C naught is just a constant. So when you take the derivative at 0, c1 times x minus a to the first power is going to be 1 times c1 x minus a to the 0, which of course becomes just c1. We don't even need that plus there anymore. So it's just c1. And then we get 2 times c2 x minus a to the first plus 3 times c3 x minus a squared, just using what we know about derivatives and the power rule. Technically, there's a chain rule. We would be multiplying by the derivative of x minus a, but on the inside, the derivative of the inside through the chain rule. But that would just be multiplying by 1. So we get c1 plus 2c2 x minus a to the first 3c3 x minus a squared, and so on and so forth. And so we can see that. I wrote that out in my typed form down here too. So what we're doing each time we take the derivative of the nth term is we're applying the power rule. We bring down the n times the coefficient, so n times c sub n. I'm trying to erase this, get this out of here. So we end up with n times c sub n x minus a to the n minus 1. So we are integrating just term by term, and we can do that in the power series. Turns out we can do the same thing with the integral. When we integrate a power series, we are integrating term by term. Now, one thing I will make note of, because this is an infinite polynomial and this goes on forever, we actually put the integration constant at the front. So this is the integration constant. So we've got that integration constant, and then when we integrate, we end up with, we're taking our power series, when we integrate, we get c naught times x minus a. Technically, you know, when we think about integration, we would normally just get c naught times x, but what we do is we write that as c naught times x minus a, because c naught times a is a constant. So I will just mention that. And then, of course, we just integrate term by term. So as we're integrating, we increase the power by 1 and divide by the new power. So we get c1 x minus a squared over 2, c2 x minus a to the third power over 3, and c3 x minus a to the fourth power over 4, and so on and so forth. And we put that integration constant in the front. I started to write that, and then I didn't finish writing the word constant. That's our integration constant. And what that ends up giving us is this little formula with the integration constant in the front, and then we have c sub n x minus a to the n plus 1, that power rule, and divide by the n plus 1, and that will generate that expansion for the integral of a power series. Now, note, what happens when we integrate and differentiate is we continue to have the same radius of convergence. So the radius of convergence stays the same when we differentiate or integrate a power series. But that doesn't mean necessarily that the interval of convergence remains the same. Convergence may change on the endpoint. So a series might converge at an endpoint, whereas when it's differentiated, it might diverge at that endpoint. So you just need to recheck endpoints for convergence, endpoints of the interval of convergence for convergence. So just remember the radius will stay the same, but the radius of convergence will stay the same, but the endpoints you may gain or lose convergence when you differentiate or integrate. Okay, let's take a look. All right, let's take a look at this power series. F of x equals 1 over 1 plus x, and we want to differentiate and find a power series for the derivative of this function and its associated radius of convergence. So what we're going to do is we're going to first say, how could this be represented as a power series? So how could this guy be represented as a power series? Well, this is one we actually did on a previous video, but I will just remind us. This is 1 minus a negative x in the denominator. So this is from that useful series. We can see that we've substituted in a negative x into 1 over 1 minus x. And so this will become the power series from n equals 0 to infinity of negative x to the nth power, as long as, remember, every time we make this equality, we also have to state when that is true. So that is true when the absolute value of negative x is less than 1. And this gives me the power series negative 1 to the nth x to the nth from n equals 0 to infinity. And if we were to write out a few terms, the first term is going to be 1, and then we have the alternating signs, negative x to the first plus x squared minus x cubed plus x to the fourth, and so on and so forth. And that is true as long as the absolute value of x is less than 1, continuing to simplify. So that's how that function can be represented. We're going to integrate it in part B. That's how that function can be represented as a power series. So if I want the derivative of that function, well, what would be the derivative just using as a power series? What would be the derivative of that function just using rules of differentiation? So what is the derivative of 1 plus x to the negative first power? And that would be negative 1 times 1 plus x to the negative second times the derivative of the inside, which is 1. So that is negative 1 over 1 plus x to the second power. So that's what the derivative would be of the function itself. But how could we represent that as a power series? Well, we know what the power series of the original function was. So that would be the same as taking the derivative of the power series from n equals 0 to infinity of negative 1 to the nth, x to the nth, which there is another way to write that. Let me get a little more screen space here. So that is equal to the derivative. Just if we were to write that out, remember we have that written out up above. That is the derivative of 1 minus x plus x squared minus x cubed plus x to the fourth, and so on, right? When we write a power series, it is representing that infinite polynomial. And it's easy enough to take the derivative of polynomial terms. So when we take the derivative, clearly the derivative of 1 is going to become 0. Let's just write this down here. So the derivative of 1 is going to be 0 minus 1 plus 2x minus 3x squared plus 4x to the third, and so on. Now, when we take the derivative, when we're looking at the power series and taking the derivative of the power series, remember the negative 1 to the n, that's just a constant on each of the terms. What we're taking the derivative of is x to the n. So when I take that derivative, that becomes the series from n equals 0 to infinity. We still have that constant negative 1 to the n, but when we take the derivative of x to the n, we get n times x to the n minus 1. And that is going to generate the series that we have in its expanded form over here. If you think about plugging in 0, the first term would be 0. Plug in 1, the next term is going to be negative 1 x negative 1, and then the next term is going to be 2 times x to the first, and so on and so forth. So that does represent it. We just did it term by term here, and here we did it in its generic form of x to the n. We took the derivative. Okay, now one last thing. So we know how to represent the derivative of that function. I'm gonna get rid of the in-between steps. We have all the steps here. The derivative of this function is actually equal to negative 1 over 1 plus x quantity squared, and that is equal to the power series negative 1 times to the n times x to the n minus 1. Now, this is what I'm going to look at right here, this n equals 0. Now, we can leave that there, but it's a little bit silly to leave it there because it creates that, to start the index at 0, because it creates that addition of 0, and that's not necessary. We don't need to have an extra 0 term. So if we have 0 terms that we're adding into a series, we can just adjust the index to start at 1 to infinity here. And sometimes that will happen when you take the derivative. You might end up, if you have a constant term, that constant term will go to 0 when you take the derivative. So you can adjust the index for that. So here is our power series representation for the derivative of the function we were looking at, which ends up being negative 1 over the quantity 1 plus x squared, and that is equal to the series from 1 to infinity of negative 1 to the n times x to the n minus 1. That was a mouthful. Now, what would be the radius of convergence? So let's add that part in because we were asked to find that. What's the associated radius of convergence? Well, remember what our theorem said at the beginning today. It said that when we integrate or differentiate, the radius of convergence will stay the same as the original function. So we already calculated that radius of convergence right here. And so the radius of convergence here is 1. So we will continue to have that same radius of convergence. So when the absolute value of x is less than 1, or another way to say that, where the radius of convergence is 1. So we will add that into our statement here. Okay, so that's how we differentiate. What if we wanted to integrate this function? Well, let's think about what would that look like if we integrated the function. Luckily, we already have the function in its power series representation. I'm just going to rewrite it here so I can zoom in. So 1 over 1 plus x, remember we showed that that up above was equal to negative 1 to the n, x to the n from n equals 0 to infinity. And of course, if we expand that out, that's 1 minus x plus x squared minus x cubed plus x to the fourth, and so on and so forth. Okay, so now let's zoom in. So what if we want to integrate this function? So what would that look like if we integrated it? Well, if we integrate f of x dx, that would be the integral of 1 over 1 plus x dx. Oh, and I want to make one more statement up here. Again, I think we've talked about this a lot, but this is for the absolute value of x less than 1, or another way to state that, where the radius of convergence is 1. So when we integrate 1 over 1 plus x, well, that's actually just a quick little, like if we want to integrate that, that would be a quick little u sub. U is 1 plus x. Let's see what that function ends up being. Du would just be 1 times dx. So this would be the integral of 1 over u du, which ends up being the natural log of the absolute value of 1 plus x plus an integration constant. All right, so what happens when we actually integrate it in its power series form? So now let's say, okay, so that's what the function is. What would it look like as a power series? That's what the integral of this function is. What would it look like as a power series? Well, what is the power series of the original function that we integrated? Well, it's the power series from n equals 0 to infinity of negative 1 to the n, x to the n, and we're integrating that with respect to x. So we're integrating, let's go ahead and write it in its polynomial form, because I think it's nice to see it in both ways. So if we write it in its expanded polynomial form, if we expand out the series, we're integrating term by term, we're integrating 1 minus x plus x squared minus x cubed plus x to the fourth. Well, what would that be? Well, when we integrate, first of all, we're going to get an integration constant. So we're going to get plus c, and then we're going to have 1 the integral of 1 is going to be x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus, and then so on and so forth. And I just put the integration constant in the front. So when we integrate a power series, we're integrating it just term by term. So again, we come back here and we look at this. This is representing a constant. When we integrate, we will get an integration constant. So we get c plus, and then we are integrating every term. And the negative 1, when I integrate it, the negative 1 is a constant, negative 1 to the nth power. That's just a constant in front. And we're integrating x to the n. So when we integrate x to the n, we increase, power rule tells us, increase the power by 1 and divide by n plus 1. So we get x to the n plus 1 over n plus 1. Now we still have the c here, but what we have just shown was that the integral of 1 over I'm going to zoom this all the way back out. The integral of 1 plus x dx, which is equal to the natural log of 1 plus x, is equal to c plus this power series. So we've just shown what it is. Now, here's the thing. Because we were able to do this integral right here, we can actually find that c. So let's find, got zoomed way out. Let's find that integration constant. Let's find c by using a value of x in the interval of convergence. Okay, so what's the interval of convergence here? Well, remember what we said at the beginning was that this would be true if the absolute value, the original function that we integrated, which will maintain its same radius of convergence when we integrate, was 1. The radius of convergence was 1. So if we pick something that has an absolute value that's less than 1, so in this case, let's let x equals 0, because that would be on the interval of convergence. If x equals 0, then the natural log of 1 is going to be equal to c plus the series from negative 1, it's actually from n equals 0 to infinity, of negative 1 to the n, x to the n plus 1 over n plus 1. But we plugged in 0 for x. So when we plug in 0 for x, 0 to the n plus 1, this whole series, when we plug in 0 for x, goes to 0, and we find that the natural log of the absolute value of 1 equals that integration constant, which is, of course, 0. And so our integration constant is 0, and we can show now, let's zoom back out to where we had the power series. We can show that our power series representation for the integral grab the wrong color there. Let me grab my black pen. The integral of our function f of x dx, which was the integral of 1 over 1 plus x dx, which was equal to the natural log of the absolute value of 1 plus x, is actually equal to the power series from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. And that will be true for the absolute value of x less than 1, or another way to say that, when the radius equals 1. So we were able to find another power series representation using one that we already had. So there's a lot of manipulation here, and I wrote out a lot of steps as we were going, but we can differentiate and integrate a function with a power series representation and come up with a new power series, a new power series representation for a new function that was the integral or derivative of the original function. So let's do one more example in this video. Okay, so let's look at this example where we want to find a power series to represent this function, the inverse tangent of x, and its associated radius of convergence. So we're looking at this inverse tangent of x, and we're thinking, what in the world? How am I going to do this? How am I going to write a power series for this function that doesn't look anything like the functions we've been working with? Well, here I put this little thought bubble, because what we have been working with is this useful series. And this series, 1 over 1 minus x, is equal to the series x sub n, x to the nth, from n equals 0 to infinity. But how does the inverse tangent relate to that function? So, we've done all kinds of stuff. We've manipulated this function in the last couple examples. We differentiated and integrated something that looked like it. We've made substitutions on this x right here. But what about the inverse tangent? Well, let me say this. What's the derivative of the inverse tangent? It's 1 over 1 plus x squared. And look at that. That's starting to look more and more like this useful series. So what we're going to do here is we're going to come up with a power series for 1 over 1 plus x squared. So we're going to come up with a power series for this guy. And if we have the power series of the derivative of a function, we're going to put that together with what we were just talking about, and we're actually going to integrate to get back to the original function, the inverse tangent. So let's do it. So this power series, we could represent 1 over 1 plus x squared, because it's 1 over 1 minus a negative x squared. And so we could make that substitution into that useful power series we've been working with, negative x squared to the nth from n equals 0 to infinity. And 1 over 1 plus x squared is equal to the power series from n equals 0 to infinity of negative 1 to the nth, x to the 2n, which we'll write out a couple of terms. That's going to be true as long as the absolute value of negative x squared is less than 1. So, of course, that's just the absolute value of x squared is less than 1, which when we take the square root, that is true when the absolute value of x is less than 1. Or another way to state that is that the radius of convergence is 1. And let's write out a couple of terms for this power series for 1 over 1 plus x squared. So the first term would be 1, and then the next term would be a negative x squared, and the next term would be a positive x to the 4th, negative x to the 6th, and so on and so forth. So we have a power series representation for 1 over 1 plus x squared. So how do we get back to the inverse tangent? Well, if we want to get back to the inverse tangent is going to be equal to my f of x that I'm looking for. My inverse tangent is going to be equal to the integral of 1 over 1 plus x squared dx, which when we do that, we're going to end up taking the integral of the power series that we just used to represent n equals 0 to infinity to represent 1 over 1 plus x squared. So that's the integral of the power series, n equals 0 to infinity. The power series is above, negative 1 to the n, x to the 2n, with respect to x. And just because I think it can be helpful to see it, let's write that out in its expanded form there for that infinite polynomial. So we're looking at taking the integral of that power series. So we're putting two things together here, right? We're taking a useful series representing a function with it, and then we're saying, well, how does that function connect to the actual function I want the power series of? It happens to be that I could integrate 1 over 1 plus x squared to get back to the inverse tangent. And so now we're going to integrate. So the inverse tangent, it turns out, is actually equal to, well, when I integrate this power series, I write my integration constant in the front because it's going to be a series. So c plus the series n equals 0 to infinity. Let's zoom in a little bit. And the integral of that power series, remember, this is just a constant, negative 1 to the n. That's the constant, the coefficient on each of the terms. So when we're integrating, we're going to be integrating that x to the 2n, the power on x, and we're going to have that negative 1 to the n. We're going to still just have that coefficient, negative 1 to the n, and we're going to get x to the, when we integrate, power rule says we add 1 and divide by the new power, 2n plus 1. And again, we could write that out. If we were to integrate the power series, it would become x minus x to the third over 3 plus x to the fifth over 5. We can see it being done with this guy term by term, minus x to the 7th over 7, and so on and so forth. And then, of course, there'd be an integration constant, but we put that integration constant in the front since it's an infinite series. And so we have a power series representation simply by using a useful series and then using integration to get back to the inverse tangent. So just one last thing that we want to do here, we want to find that integration constant, that c right there. And so what we can do is we can say, since this is true, the radius of convergence and interval of convergence stays the same through integration and differentiation. So what we can say here is let's pick x equals 0 because x equals 0. X equals 0 falls in the interval of convergence, and the inverse tangent of 0 would be equal to c plus the sum of, well, when we plug in 0 for x, it would zero out the whole sum, so it would be the sum of zeros, so that's just 0, and the inverse tangent of 0 is 0, so it turns out the integration constant here is 0. So we picked x equals 0 in the interval of convergence to find our integration constant. And what we've ended up doing here is we've ended up utilizing our useful series, our rules for manipulating power series, and our ability to now integrate a power series. I'm trying to talk and write at the same time to summarize what we just did here. And so that again is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on and so forth. And this is true when the absolute value of x is less than 1. And what we've been building on throughout this whole section of working with power series is we've worked with this one useful series and then manipulated it, and now we've gotten into, on this video, differentiating and integrating something that looks like this power series or variations on that power series. And here at the end of this video, we've even shown how we can use integration to work our way back to a function we didn't know its power series representation for, but simply through those tools that we've built up through this section for power series, we now have another, and I'm going to go ahead and give this guy some fireworks. We have another, what I will call useful series that we can build on, just like we built on that original one. And in future sections, we are going to build up a bank of, we can build off this useful, another useful series. And that's what we're going to do. We're going to build up a bank of useful series that we can work with and manipulate, useful power series for functions. Okay, I just noticed that I don't know, maybe I didn't write the one there, but I think I was trying to talk and write and do all of it at the same time. But that's when the absolute value of x is less than 1. Our radius of convergence here is 1.